Okay, good morning. Mic working okay in the back? All right. So a couple announcements before we get started today. First of all, I hope you had a delightful Thanksgiving holiday. Welcome back for the final slog. A few notes as we get going. Remember, the final homework assignment is due this time on Wednesday. We're going to finish up our discussion of the internet today. That homework will be due then on Wednesday. We will have the quiz a week from today on Monday. Just as a note, unlike the previous 6 quizzes, the quiz next Monday will be entirely multiple choice. We're sort of in a bind to get those graded so that we can talk about final grades and the final exam and everything next Wednesday. And just the only way that we're going to be able to get them graded in that sort of 36-hour window is if it's multiple choice. So just be aware of that. It will be completely a multiple choice quiz next Monday. Otherwise, we'll talk about at the end of lecture what's going to happen in the remaining class periods of the semester after today, since we should finish up our discussion today on this. And then the only other announcement that I have is to remind you that course evaluations are now open. They've been open for about a week. I really, really hope you'll take 5-10 minutes and fill out the course evaluation and tell me what you liked about the course, tell me what you think could be better about the course. I read every comment that's written, and I look forward to your feedback, and thank you in advance for leaving it. Otherwise, I don't think I have anything more to say right now. Does anybody have any questions? So basically, we are in the process of grading the term papers. There's 100 of you. There's 2 of us. This is not going to happen overnight. Certainly, it is our intent that everything will be graded by the last day of class, so that next Wednesday, not this Wednesday, but next week. Sometime probably Tuesday night, Wednesday morning, I will upload preliminary grades, which has everything. So like your last homework assignment, the last quiz, the term paper, all of that. In there with sort of what the final breakdown was, what your preliminary grade is, to then help you determine do you want to take the final or not. But we'll talk about that next week. But yeah, well, I said all of each steps would be, all of that would be posted, because we grade that when we're doing the final. It's just easiest to just sort of just go across the whole line when we're in the process of grading it. So yeah, there haven't been any grades posted because we're not ready to post them yet. Okay, other questions? Okay, then if not, what I'd like to do is sort of get us thinking again about what we did last time and recap our last lecture. So last week, before the holiday, think back to when you were 5 or 10 pounds lighter. We started our discussion of the internet. So we'd been discussing Google Maps, and we spent a bit of time talking about route finding. Okay, so Google Maps, the idea was we had all these different locations, we could make a graph, and how did we find our route, shortest route, from one place to another? And then last time what we did was we started to pivot into the internet and see that the common theme behind Google Maps and the internet is that it's all about route finding. What we're going to do today, and sort of for the new stuff that finishes up this unit, is looking at how do we actually do route finding in the internet. It's going to be a little bit different than Google Maps, and we'll discuss that in a bit. But before we could do that, we had to get into what was the internet. If we're going to understand what might be a little bit different, we have to understand what the internet actually is. And so we spent a bit of time in the last lecture, basically the entire lecture, looking at different tools that help make the internet work. We spent a little bit of time talking about different protocols that the internet uses. What was the purpose of a protocol? Anybody remember from last time? Anyone have in their notes, what was a protocol? Right, so it's basically a way of turning instructions into a computer-readable format. But more than that, what the protocols actually did is they allowed cooperation between the devices. This is what set in place sort of how do the devices communicate? What's that context for communication? If you send me a message or a request, how do I respond? And this is all codified through protocols. Okay? And so the example that we had sort of here is you could think about 2 people having a conversation. Person 1 there on the top left comes in and says, hi. Person 2 responds back, hi. Then the person asks, what time is it? Okay, well, in the figure, it's 2 o'clock. Okay? Computers do the same thing. When we're trying to do communication, like getting a website from a web server, what our computer is going to do as soon as we hit the enter button on our web browser, what that's going to do is send basically this hello message over to the web server, just saying, hi, I want to communicate with you. That server is then going to send an acknowledgement back sort of saying hi, the second person. Once we've got those communications open, then we send the request and say, can you please send me this web page? And then assuming that the server knows what the web page is, everything works okay, they will then reply back with the file, which is that website, maybe any of the images or text that goes along with it. And then our web browser takes that and can display it. And that's the end of the communication. But that's the idea here, that there are all of these different protocols behind the internet detailing how do the different devices communicate with each other, how do we do error diagnostics. We looked at some of the error codes for HTTP. We had the Hypertext Transfer Protocol. And so in these protocols are different error diagnostics so that we could see, well, here's your web page, everything worked just fine, quote unquote, the error 200. We can get bad requests. We've got permission denied. You've all seen the error 404, page not found, that said you requested a web page that doesn't exist. The web server has no idea what you're talking about. Okay? And that's happened to all of us before at some point. But the idea is that this HTTP, that Hypertext Transfer Protocol, is one protocol that's used on the internet, and there are plenty of others. To then start to understand how all of these different protocols work together, we divided the internet into layers, okay? With the idea that there are several layers that work together that help make everything work. So if we go back up a few slides, the three ones that we spent most of the time talking about were the numbers 1, 2, and 3 here on the slide. We had our application layer, which is pretty much where you interact. The purpose of the application layer is to turn whatever you want to do on the internet into something the computer can understand. So for instance, you have your web browser. Well, you want to get a web page. You open up your web browser, you type in the URL into the bar, or you go to Google and do a search and then click on whatever the link is. But that's how the web browser knows you want to get that web page. It then takes care of doing all of the HTTP, of saying, send the message over to the web server, wait for the response, request the web page. When you get the web page back, display it. Did you have to think about any of those details? No. All you had to do was click the enter in the URL bar, and it went and did all of that for you. But that's the purpose of the application layer. Take whatever it is you're trying to do and convert it into something that computers can work with and manage. Transport layer, being the next one down, was what manages sort of all of the incoming and outgoing communications from your computer, with the idea being that your computer typically is only connected to the internet in one way. Either you've got a wired connection, or wirelessly you're connected to some wireless router. But could you have multiple applications running on your computer that are simultaneously having to access and use information from the web? Sure. Maybe you've got multiple tabs on your web browser open. Maybe you're streaming music on some other application. Maybe you've got some online video game going, and maybe you've got an email client or email server running in the background. Hopefully it doesn't have classified information on it. Okay? But the idea is your computer's got all these, but there's still only that one network interface that actually links your computer to the internet. And the purpose of the transport layer is to make sure that all of the communications to or from your computer get routed to the appropriate application. So when you make that request on your web browser is going to form the message to say either hello or send me this web page or whatever, and it's going to send that down to the transport layer. The transport layer is then going to mark it as saying, well, this type of communication came from Chrome, or came from Firefox, or came from some internet streaming, came from Netflix. You've got your Netflix app running. Okay? And it's going to mark it as that so that it knows where does the communication go. The transport layer is then going to break up that message into lots of little packets. Think back to our data transmission unit, because the smaller these messages are, the better control we have over fixing any errors that occur in transmission. And after the transport layer has chopped them up into these little packets, it's going to send them down into the network layer, which actually then tries to route the packets from our computer all the way to Netflix's server or whatever web server that has the web page that we want to access. Okay? Likewise, then, when our computer receives a message, so we sent that request for a web page off to the server responds and sends us back that web page. Transport layer at our computer is going to be the first thing that receives all of those pieces. So it's going to get all of those packets, which is, again, our web page broken up into all of these little pieces. It's going to reassemble them and put them in order. And then it's going to recognize, oh, this is a web page that needs to go up to Chrome or Firefox or Opera if you're lightweight, whatever web browser you're using, and send that and forward it up. And instead, it knows better than to send this web page to Netflix. What would happen if it tried to send your web page to the Netflix app? Anybody have any ideas? Presumably, Netflix would try to play it. It would interpret that as streaming video, so you're probably going to get some really awful picture and some really screeching noise. Okay? But the idea is we've got this transport layer in there working on our network card to make sure that that doesn't happen. Okay? And so then last, we have our network layer, which actually tries to then move the data around. Network layer no longer cares, is this a web page? Is this data? Is this streaming video? Is this video? It doesn't matter. All the network layer has to know is there's data that needs to go from this computer to another device somewhere on the internet, and somehow we need to figure out how to route that message through the World Wide Web. Okay? There's also the link layer and the physical layer. These get into a lot of electrical engineering and computer engineering stuff, and we don't have a whole lot to say about those in terms of actually how do you physically move the bits from one device to another. Okay? But this is the idea of the internet. Does this sort of sound familiar? I know it's been a while since we've thought about this, and we've had a lot of really good food in the meantime. Okay? So then what we're going to do today is look quite a bit more at the network layer to see how do these messages actually get moved around. How can we algorithmically try to develop a way to get that message from our computer over to some other device on the internet that needs to get that data? Okay? And so in this sense, it turns back into this route finding example, and that's sort of the common theme again here between the internet and Google Maps. So we already saw from last time, again, just to recap a little bit, that when we're thinking about the network layer and looking at routing, we can basically treat the internet as a graph, where we can have all of these different vertices throughout our graph, where the vertices might represent, what would the vertices be on our graph? Different devices on the internet. And so then the edges along our graph would be direct connections between the devices. So we have our laptop up here that's running this presentation. This laptop does in fact have an Ethernet cable plugged into it. So there's probably some direct connection from this computer to some router. I don't know, it's somewhere in this building. I don't know exactly where it would be. This computer might also be connected to Wi-Fi. I don't know, I haven't checked the settings. Okay? So there might actually be two connections to the internet from this computer, but most devices are only going to have one. You're either wired or you're wireless. Okay? And so this is sort of down here in this institutional network where we can see a lot of these things. We can see sort of here are our computers that are hardwired. We've got our different laptops that go through some wireless router, which is then hardwired into the internet. We can have all of this infrastructure behind the scenes that sort of connects everything together. And you could think about sort of this big blue blob down here, this institutional network, as being Stony Brook. We know that the campus has its own internal network. It has its own firewall to try to protect from the outside if there are malicious things going on elsewhere in the world. And sometimes, believe it or not, we might, from on campus, want to access something that is outside stonybrook.edu. Anybody done that this morning? You've accessed a website that wasn't stonybrook.edu? Okay. So what happens then is we have to go out and we'll go to some regional ISP, ISP being an internet service provider. And so maybe, this is probably something Long Island, New York City, tri-state area. It's probably Optimum in a lot of cases around here. And then that's going to maybe network into, well, maybe there's other people's homes or small businesses locally that we might want to get at. If the web page we're requesting isn't local, maybe we want something from, I don't know, Australia, we're going to have to then pass up from our regional ISP up to a global ISP, which will then try to route that message into a regional ISP for Australia and somehow pass it along down to the devices. But we have to figure out how do we get through this sprawling network of all of these devices to get our message from us to Australia. Okay? So we also looked at a couple tools last time to try to understand how this works. And there were some neat things. So one of them was this program called Ping, and this is basically where we ended last time, where if you pull up a command prompt on your computer and you could try to ping and put in a URL, we did ping of google.com last time, we could look, and what this program is trying to do is to time how long does it take a message from your computer to reach the targeted destination and then for an acknowledgement to come back. So this actually gives, Ping was actually going to give you the round trip time. It's not just the time, it's the round trip. but we can try to time this and see what's going on. And so what ping is going to do is send several packets out into the internet, just little pieces of data, and say, oh, well, when you receive this, send one back to me. Okay, so we send our packet out to Google. It routes its way through the internet, through the network layer. Google gets it, and this is part of a protocol. Ping would have its own set of protocols for how the application works. Google receives that and says, oh, we just got pinged. We should send a reply back. Okay, so then Google goes, sends a reply saying, we got your ping. It routes its way back through the network to us, and our computer times how long did it take from when we sent the message to when we received that message, and it will display that data. Okay, and it'll sort of keep doing this some number of times, and you can get an average value if you want it. And I believe one of the homework problems has you look into this, dealing with computers that are maybe a little bit more locally versus ones that are not so local, to look at some of the different times that you might get when running through the internet. The other program that we can do, and again, we saw this very briefly at the end of lecture last time, is this idea called traceroute. So on Unix or Mac, it's actually the words traceroute smashed together. Windows was feeling thrifty and got rid of the O, U, and E in route. So it's traceroute. And what this is going to do is go a little bit beyond ping and not only time how long did it take that packet to go to the destination and come back, but it's also going to try to give you sort of some breadcrumbs. What path did the packets take? Okay? And so in this sense, you can start to see, you know, how many steps, how many different devices through the internet did your message have to take. In certain cases, you might learn where did the things go. In a lot of cases, you're just going to see IP addresses for the various hops along the way, which are not necessarily that informative. Every now and then, one of them might actually get translated back into a URL using those DNS servers that we talked about last time. And you can try to maybe see how does this message hop through the internet. Okay? But it's sort of neat. If you want to see how the internet actually works, these tools are available to you. They come pre-installed on all machines these days. Just open up a command prompt, and you should be good to go. So that's sort of the 10-minute recap from last time. Does anybody have any questions before we dive into some new stuff? Okay. Then we finally come to the crux of this. How is the internet different from Google Maps? So we already spent some time 2 weeks ago looking at route finding in Google Maps, where we had, here was our big map, here were our cities, here were the routes between them, and we could use what to try to find the shortest path between two places. What did we do? Oh boy, next week's quiz is going to be fun. It was some type of algorithm. What was the name of it? Oh boy. Okay, well, we'll find out next Monday. Okay, so now what we want to do is start to focus now, contrasting Google Maps with the internet. What's a little bit different? Can we use unnamed algorithm from last time to do route finding through the internet? Could we use that algorithm? It which shall not be named? Okay, so one of the observations is physical locations. So where are the different cities don't change as often as the internet does. Okay, so New York City is more or less in the same location today as it was 2 hours ago. Okay, everybody okay with that? Okay, so the idea is the web is changing more dynamically. Does that have an impact on how we need to do route finding? Okay, so if our graph changes, so suppose now a route between two places changes, or a city or one of our destinations moves, how would we have to redo Google Maps? What would change? Is there an easy way to account for that information in the algorithm that we won't name that we looked at 2 weeks ago? Or would we basically have to just start over and do the whole thing again? We'd probably have to start over and just do the whole thing again. And so if everything is changing very rapidly, this is going to get expensive. That algorithm was really good at finding those routes when the graph was static. When that graph just sort of, we had our map, we had our routes, here was the thing, we could run it once and have everything that we needed to know. But if that graph is now changing fairly rapidly, In principle, in a theoretical world where we didn't care about algorithmic cost, it would work just fine. But in the real world now, where the web is changing, and every time there was one of those updates, we would have to rerun the routine, this is going to start to get prohibitively expensive. And so one of the key differences between the internet and Google Maps is that the internet is just much more dynamic. Websites are updated. New devices are added to the internet constantly. Devices are removed from the internet, or devices move on the internet. So you're sitting here right now in this class, you've all got your phones, some of you have tablets and laptops open, and you're connected to the internet through a wireless router. There's probably one, if you look up on the ceiling, I'm sure you'll find one somewhere around this room. I don't think we actually found it last time. I guarantee you there's one in here. Oh, it's, okay, I just can't see it. It's up there. Okay, you go to your next class at 11 o'clock in a different building, your computer is still connected to the internet, but is it connected at the same spot? No, you're going to be accessing a different wireless router, and so if someone's trying to find your computer on the internet, what's changed? Your location. The whole connectivity of that internet, at least with regard to where your computer is, has moved around. And so we're going to need an algorithm that can deal with that sort of dynamic changing. Okay? Whether the device is added, removed, or just changed location. That happens. Different components of the internet can spontaneously break. We discussed briefly last time that there was all this infrastructure behind the internet. There were all these routers and switches and things between your computer and another computer on the internet. Is it possible one of those devices breaks? Yep. Is it possible it loses power? Yep. So we have to deal with that too. This is the World Wide Web. What are the odds that at any point in time some router on the internet doesn't have power? Probably pretty good. Okay? And so we need to deal with that in real time to make sure that we can deal with that, we can adapt to it, and still get our message routed through the internet. And then the other observation that was made is that the internet is substantially larger than our transportation infrastructure. There are probably billions, if not more, of devices on the internet. And so if we're going to run that algorithm that we're not naming, do we need to know the full graph to be able to do that? Yeah. Is it practical to know the full graph of the internet? Even if it was static, it wasn't changing all the time, but we said, you know, here is the internet at 8:50 this morning. Is it practical to know that entire graph? No, it isn't. So we're going to need to do something a little bit differently when we're thinking about route finding, because that algorithm, while it would work in theory, is in practice not going to do very well. Oh, there's the name. It shouldn't be there. Okay. So Dijkstra's algorithm that we discussed a few weeks ago is what we'll call a centralized algorithm, in the sense that the person or computer using it has complete knowledge of the graph. There's sort of this one omniscient being on top of everything who's able to look at the entire lay of the land and try to then figure out what are the shortest paths that we should take. Okay? And so there's this one central authority that can help us find the shortest distance from New York City to San Francisco. When we're looking at the internet, is that centralization going to be okay? No. We're going to need something that's much more decentralized, where there's not sort of this one single authority, because number one, the internet's changing too frequently that one single authority would have to be really, really quick. And number two, it would need to be really, really big central authority. So when we start thinking about routing algorithms for the internet, we're going to want one that's decentralized, which is to say no one has to know the entire graph of the internet. Maybe we only know our little local corner of it. So when we're thinking about our laptop here, this laptop may only know that it's connected to one router through the Ethernet cable and the wireless router up on the ceiling. That might be all it knows about the internet. Okay? Maybe it knows one device further. It knows its next neighbors. Beyond that. So what is that wireless router connected to? What is the Ethernet router connected to beyond that? Maybe it knows that much information, but probably not much more. Okay? And so that's the idea of a decentralized algorithm. What do you think it means if we want our algorithm to be, quote, fault tolerant, unquote? Why might we want, what does that mean and why might we want it? Right, so the internet is this dynamic thing that's always changing with devices being added, subtracted. Every time something changes, we could think of that as a fault. So all of a sudden, we figured out from last time that here is a path to get from our computer to stonybrook.edu. but suddenly one of the routers goes down. I don't know, they lost power over in heavy engineering because some mechanical engineering student did something they shouldn't. Okay? Is that plausible? Yep. So now we're trying to send our message through again. Do we keep sending through this path that we now know is not going to work, or do we try to react and route around it? Well, we try to react and route around it, and that's this idea of fault tolerance. There was some fault in that path. Something happened, and it no longer is viable. If we're tolerant of that, we can try to adapt and move our way around. Okay? And so we're going to want now for the internet this algorithm that is both decentralized and fault tolerant. Okay? That's going to be really key to deal with just the fact that the internet is a different beast than physical locations and the maps. And then, of course, at the very end, we still want an algorithm that finds the shortest path. Okay? Do we want our message, if we're going to go from this computer to stonybrook.edu, knowing full well that we're on Stony Brook's network, do we want our message going to Australia on the way? No. That just seems silly. Okay? So we're still going to want our route finding algorithm to get the shortest path, or at least a relatively short path. Are we necessarily going to notice or care if it's not exactly the shortest path? No, probably not. If it takes 3 milliseconds instead of 2 milliseconds to get your web page, are you going to care? Are you going to be writing hate mail to Optimum saying you need to do better and why is my internet so slow? Probably not. You wouldn't even notice unless you're sitting there running the ping program. Okay? So what we're going to do is have a little bit of an example. As we're working through, we'll go through the full algorithm here in a little bit. The takeaway message from today's lecture is that the internet is completely held together by bubblegum and paper clips. If you don't believe that now, just wait. But what I want you to do, and this is why we have the special sort of seating request today, is I have messages intended for 9 of you. There are people's names written on these sheets. I have necessarily no idea where you're seated, but I have the message to you. And so what I want you to do is learn the names of maybe the 4 people closest to you and try to figure out. So again, we've got the idea that people whose last names start with the beginning of the alphabet are probably closer to this side of the room. So A's, B's, C's are here. Things in the middle of the alphabet are in the middle, and then maybe people with last names closer to the end of the alphabet are on this side. I'm going to randomly distribute some of these messages to people in the class, and the idea is every time you get one of these sheets of paper, take out your pen or pencil and put a tick mark on it. It's going to count how many people have to receive this message before the message is received by the person it's intended for. So if you're one of the 9 people and you get a message with your name on it, just raise your hand so that I know it's received and count up how many tally marks it took. Okay? So this is actually a pretty good approximation to what the internet is doing. Because again, do you know necessarily where all 100 people are throughout the room? No, you know you're sort of 4, maybe 5 neighbors. And you're going to make an educated guess where, oh, this last name comes in the alphabet before mine. I should maybe pass it to my left. Or maybe behind you or in front of you. Don't forget that there are people behind and in front of you. But that's the general idea. So I'm going to distribute these, and we'll give this a few minutes to see how long it takes messages to find their intended recipients. Oh, we already got one. That didn't take very long. Yeah, if the first person tick also, yep, count, because I'm the sender. The rest of you are all intermediaries. It's just a name. Pretend there's a message saying you're awesome. I don't know. Okay, so one of the messages has already found its recipient. How many people did it take? Took 2. Okay, so I was fairly lucky, if you will, when deciding who should initially get that message. Okay, we've got another message. How many hands did it take? Only 4. Okay, that's not too bad. If you're curious, I pseudo-randomly chose the names on the sheets. We'll come back to what I meant by pseudo-random in a moment. Okay, we've got third person. How many handoffs? 6. Okay, that's not too bad. 2, 4, 6. Okay, who's going to go for 8? So for a couple things to start thinking about as we're doing this, I said at the beginning what I was hoping for is you would sort of seat yourselves in this way. Is there any guarantee that if you get a message and it's intended for a person with a last name before yours in the alphabet, is there any guarantee they're actually to your left? No. They could be in front of you. They could be behind you. Could they actually be to your right? Yeah, we didn't rigorously sort everyone. So, maybe passing to your left isn't always the best idea in that case. Okay? Second idea. What do you think on this one? I said I pseudo-randomly chose. Do you think every one of those sheets corresponds to a person actually in the room? Is it possible we have a message destined for someone who's not here? Could that happen in practice? Yeah, it could. And so what's going to keep happening to that message? Just going to keep going around and 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 around. So I'm guessing there's one of them that's starting to amass some good amount of tally marks at this point. There might actually be a couple. I'm intrigued that the one I just deliberately planted one person away from its recipient has not been received yet. Good job learning the people's names next to you. Okay, so we still got a few messages going around. Has anybody gotten the same message twice? Okay, there's a few people. Can that happen in practice? Yeah, it could. Okay, so is this maybe an optimal way to try to find and give messages? No, it's not. So the internet is maybe a little bit smarter than this, but not much. Okay? Do we want to wait another minute and let people try to get their messages? Okay, so let's maybe wait one more minute, and then we'll sort of just stop those messages where they are. Just ask how many ticks do they have on them. Well, what if the person I chose just didn't come to class today? I sort of seeded one that I assumed that would be true. But just to say, it might be a name from someone that was in the class last semester. Or next semester. I already have that information too. Okay, so I guess at this point, if you've got one of the messages that's still circulating around, just hold on to it for a minute. How many tallies are on it at this point? If you count them up. Just 31, okay. 22, 24. Okay, one's still getting passed over there. 22. Okay, so we can see, some of the messages found their recipients pretty quickly. There was a 2, there was a 4, there was a 6. I'm sort of disappointed there wasn't a 1. I tried to make that happen, but apparently I failed. Okay, but there's still messages floating around. All right. So, I guess if you want to try to keep floating those around the rest of the class, we can, but we're going to move on with the lecture at this point and see that. But this is to a pretty good approximation what the internet is actually doing. Okay. So what ends up happening is there's this one key thing that the internet is doing when trying to figure out how to pass messages. And this has to deal with this idea of what's called the Bellman-Ford equation, which has sort of this name. Of course, the Bellman-Ford equation was named for Dr. Equation. See, you're perking up. I know it's Monday morning after the holiday, but it's okay to laugh. It's fine. Okay, and so the idea here is what the internet is going to do is say, I know all of the devices that are immediately adjacent to me. And so if I get a message that's not destined for me, I am not the destination, I have to pass it to one of my immediate neighbors. Because that's what you had to do. You got a message, it's not you, figure out one of the neighbors to pass it to. The question then is, which neighbor do I pass it to? Can you make some sort of informed decision? Well, in your example, you would say, oh, well, this last name is sort of after mine in the alphabet, so my informed decision would be pass it to the, well, from your perspective, my left, your right. Okay? And so that would be maybe what you do. What the internet is going to do is something maybe a little bit more quantitative, where what they're going to do is say, well, I'm X, I'm device X, and I have a message that's destined for device Y. Well, what I'm going to do then is say, well, I know I have all of these neighbors. Let's symbolically just call one of them V, and we're going to sort of look at all of those neighbors V. How much does it cost for me to directly send my message to V? So that's going to be what was maybe the cost of sending it from our computer up to the wireless router, or from our computer to the wired router, whichever way we're connected to the internet. And then what we're going to do is sort of ask device V, how much do you estimate the cost is going to be to forward that message on to Y? And there's a key word there, which is to say estimate. Okay? So what we're going to then do is look over all of our neighbors to see, well, if I pass it to device 1, what is the estimated cost total to get it to device Y? I could pass it to my other neighbor and try to estimate what's the total cost to get it to device Y. At the end of looking through all of that, which one do I actually want to send the message to? Whichever neighbor gives us the least cost. Okay? And that's basically all this is saying, is to say, look at what is the cost to directly send it to our neighbor, that's this D term, add on what's the estimate that our neighbor will forward it on to Y, and choose the one that has the least cost. That's the neighbor we pass it on to, and what do we then do? We send the message to that device. And what does that device do? The exact same thing. First of all, it's going to ask, am I the destination? If it is, what happens? Done. Messages receive the destination, and we're going to pass whatever that information is from our network layer of the internet back up to the transport layer, which will forward it to the application layer to do whatever it is that needs to be done. Okay? But that's all that's going on. And so you might notice that this Bellman-Ford equation was sort of tacitly used in Dijkstra's algorithm when we were looking for those shortest paths. Now we're going to make it a lot more explicit. Okay? Questions on this? All right. So how does this equation help us? I mean, it seems kind of obvious. If I have a finite number of choices to pass the message to, well, then sort of query what's the cost associated with passing to each of those neighboring devices and choose the least expensive. That seems fairly intuitive. So how does this actually help us get to a decentralized routing algorithm? Well, notice what we needed each device to do was to have some sort of estimate. So we had our cost from getting X to Y. That's our estimate. How long does it take us as device X to get something to device Y? And to be able to do this, we had to know the estimate. How long does each of our neighbors think it will take to get to device Y? Okay? So what we're seeing is that each individual device on the internet needs to have some sort of knowledge of the estimation of the costs of these different routes. Okay? Did anybody have to know the entire graph in this case? No. All I have to know are who are my nearest neighbors and what are the estimates of routing things through the internet. Do I know what's beyond my wireless router? No. Do I really care? Not really. Okay? So, what this ends up coming down to is we don't need to know the complete path. All we're going to know is if we're sending a message to Y, who do we hand that message off to? Which of our nearest neighbors? That's the only part of the path that we're going to care about. Okay? And so all we then also need to know is then what are these estimates? So toward our algorithm, what we're going to do is have each vertex in our graph, which is to say each device on the internet, store what we're going to call a distance vector, which is basically this estimate. Okay? What is the estimated cost of sending a message from us to some other device on the internet? And which of our nearest neighbors do we send the device to along that path? And those two things together are going to make up the distance vector. And the idea now that leads towards this decentralized routing algorithm is that these neighboring vertices, which is to say these directly connected devices, are on occasion going to exchange their distance vectors and then redo the Bellman-Ford equation to update the estimates of these costs. With the idea being that if we keep doing these updates, we keep exchanging these distance vectors, will we eventually converge to the shortest route? Yeah, we should. Okay? It might take a little while, but we'll get there. And so to see this, what we're going to do is we can now sort of make this into a decentralized routing algorithm, and we can specify some steps that we're going to have to do, and there will absolutely be an example here on coming slides. So what we'll do is at the beginning, what information do we know? So we're device X. We know that we are connected to, I don't know, let's say 2 or 3 devices, some fixed number, and we know the cost it takes to actually push the information from our computer here to the wireless router we're connected to. Do we know anything beyond that wireless router? Not a clue. Okay? So what we're going to do is when we initially start our distance vector, we're going to populate it with routes that say, well, I know our direct connections, and we know those costs, which is say, do we know a path from this computer to the wireless router? Yep. And we know that it has a cost of whatever that cost is. And so this is how we're going to initialize all of the device's distance vectors. It's just by look at all of the paths that we can form just from direct connections. Is this going to be even remotely close to the final answer? No. Because what are the odds on the internet that you're directly connected to the device you're looking for? Basically 0. Okay? I can't say it never happens, but I wouldn't bet money on it. And so then what we're going to do, as we've already sort of said, is that these neighboring devices will exchange their distance vectors, and that in principle allows us to better refine our estimates to see excuse me, how long or what's the cost, do we think, of trying to get the message from us to some other device, regardless of whether we're directly connected to it or not, and what's the next device we should send that message to on the way. And as we keep doing these exchanges, we're going to get better and better and better estimates. With the sense that step 4 here, if we find a shorter path. So we look at our distance vector currently says the best estimate we have of a path is cost 10 going through device 1. Well, from looking at these distance vectors, we could now go through device 2, and there's a path of estimate 8. We would update our distance vector to say no longer send the message to device 1, but send it to device 2, because that had a shorter path or a lower cost. And then we're basically going to just keep exchanging these distance vectors until there are no more updates. Eventually, we will converge to those shortest paths. Just as a note, there is a pretty detailed example, much more so than what we're going to work here on Wikipedia, but also know that it's a little bit more sophisticated than what we discussed. They go a few steps beyond what these were. This is sort of the simplest implementation. You can make this a little bit more sophisticated if you wanted to, but there's a nice example there if you're curious. And so what we're going to do for our example is consider a very complicated website or internet of these 4 devices, W, X, Y, and Z, that are connected in this way. And so notice we'll have maybe a cost of 10 to connect W to X, 2 from X to Y, 3 from Y to Z, 4 from W to Z, etc. So first of all, we see we've got a graph. Is it weighted or unweighted? It's weighted, just like before. And what does the weight tell us on those different edges? That's the cost of pushing the data from one device to one of its nearest neighbors. Is it a directed or undirected graph? In this case, it's undirected. Could we conceive of a situation in the internet where it maybe is a directed graph, where there are certain devices that you can only send to or that only send information out? Yeah, conceivably. We're not going to get into that here, but it could happen. And we'll ask the question, even though it's maybe not so important in the grand scheme of things, is the graph cyclic or acyclic? Anybody see any cycles in this one? Yeah, this is cyclic. What do you think? Is the internet going to be cyclic? Oh yeah, very, very much so. That's part of what allows the fault tolerance to happen. If there were no cycles in the graph and one of the devices goes down, would there be another route for you to get across? No. So we're going to need these cycles to help bring in that fault tolerance a little bit later. Okay? And so what we're going to do at the very outset, so we just connected these devices, okay, and we've just turned them all on. Well, so what we're going to do now is have each device set up its own distance vector. So we'll have here on the top, this is device W's distance vector. Okay? Device X's distance vector, Y's distance vector, and Z's distance vector. And the way we initialize it, again, is we look and see, well, what devices are we directly connected to? So if we look at device W is connected to how many other devices? 2. It's connected to device Z over here and device X. And so we notice now, okay, as the trivial step, what's the cost of sending a message from device W to device W? It's 0. You're the destination. Why are you asking this question? Just send the message onto the application and move on with life. Okay? But what we see then from these direct neighbors is there is a path to device X. We know how to get a message from W to X with a cost of 10 by sending that message directly to X. Okay? We also know there's a path of cost 4 to get to Z by directly sending the message to Z. And at this initialization, does device W know how to get a message to device Y? No, because there's not a direct connection. And so just as we had with the Dijkstra's algorithm, we'll just put an infinity there to symbolize the fact that we haven't actually seen a path. Okay? Which is to say the moment we see a path, its cost will be lower than infinity. Okay? And we can do the same setup for devices X, Y, and Z by looking at those outgoing connections. Which devices are they directly connected to, and seed those paths into the distance vector. Okay, so if we come back up, now that we're done with the initialization, what we're going to now do is have neighboring devices exchange their distance vectors and do the updates. Okay, so why don't we, just as a start, suppose that devices or vertices W and X exchange their distance vectors. So what's going to happen is W is going to get device X's distance vector, and that's going to give some new routes that we might want to consider. Okay? And so maybe we update accordingly. So we come back, we look at our Bellman-Ford equation, and so what we're going to do now is suppose we send our message from, now let's say from W, because that's where we're starting, to device X. And we want to know, to get to some other website, we now have to say, well, then how much did device X think it would cost to get to that other device? Okay? So we're saying, assume W sends the message to X. Well, from X, can we get back to W? Yep. And what would the total cost of that path be? 20. So we would have to add, there's a cost of 10 from where we sent our message to X. And then X estimates there's a cost of 10 to send the message back to us at W, which leads to a total path of length, or of cost, 20. Is that the best path to W that we've seen so far? No. We are W. There's a path of length 0. So do we care about that path? Not even remotely. Okay? So now we look at device X. So we send with a cost of 10 to device X. How much does device X estimate it will take to forward a message to device X? Well, 0, because that's device X. That's the destination. Okay? So that's in total a path with cost 10. Is that better than the path we already knew? No, in fact, it's exactly the path we already knew. Okay, so do we have to update anything? No. Okay, now let's look at device Y. Previously, we don't actually know a route to device Y. Okay? So we look at this now. So we forward our message on to X with a cost of 10. And X estimates how much cost to forward on to Y. 2. So do we see now a path to get to Y? Yes. And what's its cost? 12. Is that better than the path we've already seen? Yeah, as which to say we actually have a path. So we were now going to update our distance vector here. And so instead of having this infinity under Y, what's the cost of this path that we've seen? It's 12. because it cost us 10 to send it to X, and then X another 2 to send it on to Y. And what then is the device that we want to hand our message off to on that path? Well, we send it to X. We knew there was a path of length 12 when W sends it to X and then X sends it to Y. So we would update this table to now say we found a path of 12, of cost 12, and X is the next device on that path. Okay? And then lastly, you can see, if we go back here, there's no update for Z because we would say, well, let's forward our message to device X and see, well, what's the cost to get to Z? X doesn't actually know how to forward it to Z, so will there be any update? No. And then likewise, going through, we'll also see, if we were to now consider what's happening from device X's perspective, where now device X gets device W's distance vector. And so what we'd now be considering is X sends the message to W, and W forwards it on. Okay, so if X sends a message destined for W to W, W then gets it. That's a path of length 10, or cost 10. Any better than what we've already seen? No. Obviously, X shouldn't really be considering what to do with the message destined for X. You should just realize you're the destination, process it. But when X now wants to send to Z, it says, well, let's forward that message to W. Does W know how to forward a message to Z? Yeah. And it estimates a cost of 4, which leads to a path with how much cost now for X to forward on to Z? 14, because we've got to send it the 10 to get to W, and then the 4 over to Z. And what's the next device in that path? It'd be W. So after we sort of do that exchange, we can now update our distance vectors to fill in those 2 new paths that we've seen. Okay? And so what we would now do, that just considered this one pair of exchanges. How many other exchanges would we have to look at? Oh, there's a question. Okay, so there's a shorter path to Z going through Y. We haven't discovered it yet. As we keep doing these swaps, we will eventually discover that path. But what we're doing is we're looking at right now, as of what we've seen so far, this is the best we're able to do. And this is the idea that as we keep exchanging this information, it's all sort of going to spread throughout the entire graph, and we will eventually find the shortest one. But in that particular step, all we did was look at X and W. Okay? So the next thing we're going to have to do is also look at, well, X and Y are going to have to exchange their distance vectors with each other. Y and Z are going to have to exchange their distance vectors with each other. Z and W are going to have to exchange their distance vectors with each other. And we can go through this same step of saying, well, when we get the distance vector from a neighboring device, examine what's the cost of potential routes. Well, we add the cost to send our message to that device plus the estimate that that device provides us, and that's now a potential path. Is it better than what we've already seen? If yes, update our distance vector. If no, ignore it. Okay? And so we can go through a full round of this. And just exactly as you noticed, so like when device W exchanges with device Z here, we're going to discover there's a route to Y that has a cost of 7. Is that 7 better than the 12 that we had seen going through X? Yes. And so we update our distance vector to say we now know a path of length or of cost 7 where we sent our message to Z. Okay? And so after we've gone through one round of all of this stuff, we get a distance vector that looks, or a set of distance vectors that looks like this. It's nice to know, at least in this simple example, that there are no more infinities. We now at least know a path from every device to every other device within just one round. We can sort of eyeball this. Humans are good at this. Are these necessarily, or in this case, are these actually the best paths? In some cases, yes. But we might look here, and we can eyeball. W going to X says there's a path of 10, cost 10, going through X. Is that, when you eyeball this graph, is that the best path? No, it's not. We actually would want to send from W to Z to Y to X. That would give us a cost of 9. But we haven't seen that path yet. So how do we see that path? We keep exchanging the distance vectors. Because the reason we hadn't seen that, well, when W exchanged with Z last time, and come back up here, did Z know a route to X? No, it didn't. So did that information come back and help us identify that that's a good path to get to X? No, because Z's like, I don't know how to get anything to X. If you're sending to X, don't give it to me. Okay? But now, after this first round, does Z now know how to send a message to X? Or at least have a path to send something to X? Yeah. So if we go and we exchange these distance vectors again, so we look and let's say W gets Z's distance vector. When we look at X, so there would be a cost of 4 to send the message from W to Z. And then how much does Z estimate it will cost to forward that message again onto X? Well, now it says there's an estimate of 5. Well, 4 plus 5 gives us a path of length, or of cost, 9. Is that better than what we've already seen? Yeah, it is. So we would update this distance vector, sure enough, and we'd say there's a 9, and the device we want to send it to is Z. So even though in this case we're directly connected to X, are we ever actually going to send a message in that direction? No, it turns out that's just a really expensive link. There are easier ways to do it. Okay? And so you notice here in this case now, W's distance vector, no matter where it's going, W's just like, I'm going to give it to Z. At least in this simple example. Okay? But this is the idea. And so we just keep going and keep exchanging these distance vectors using that Bellman-Ford equation to then try to see what are the potential paths that we see. Are any of them better than what we've already seen? Okay? At this point, if we look at this table at the end of sort of 2 rounds of these exchanges, and again, we're omitting some of the work because we're only looking at sort of 1 or 2, but at principle, each round, there's 4 pairs of exchanges. W and Z, Z and Y, Y and X, X and W are all exchanging. So there's a lot of work going on behind the scenes. This is really tedious. Okay? But now at the end of 2 rounds, if you sort of eyeball these distance vectors, are these the best paths? Do you see sort of, as a person looking at the simple graph, do you see any better paths than what's indicated here in the distance vectors? I don't. How would our algorithm know that? Do you think? How would our internet route finder suddenly realize these are the best paths and there's really not any more work to be done? Nope. What would happen if we did another iteration of the distance vector exchange? We'd get the exact same results. If we found all of the best paths, if we keep exchanging the distance vectors, are we going to find any better paths? No, because we've already found them. And so we know that the algorithm is done if we do another round of the exchange and there are no updates to anyone's distance vector. That tells us we've basically found all of the best routes. Okay? And so in this way, have we now arrived at a decentralized routing algorithm? Yeah. Did anybody have to know the entire graph? Nope. Device W only had to know it was connected to devices X and Z. But yet we were still able to use that information and arrive at these shortest paths to get from W to any of the other vertices, or frankly, between any 2 vertices. Okay? Any questions about that? Okay. So as we mentioned, that was really tedious. Those exchanges are sort of painful, and there's a reason why stuff like this does not appear on the homework assignment, because this is just way too tedious. Okay, but the key points is that no vertex had to know the entire graph. No device has to know the internet. No vertex even had to know the entire shortest path. Again, when we look at these distance vectors, if W wants to send the message to X, all W knows is that the next device on that path is device Z. And so device W would forward the message to Z. Z then gets the message and says, oh, it's going to X. Well, Z looks at its distance vector and says, well, if we're going to X, the next device on that stop or on that path is Y. So Z forwards it to Y. Y gets it and says, oh, we're sending it to X. The next device is X. X gets it and says, hey, I got a message. Cool. End of story. Okay? And so the reason that we'll say, again, this is decentralized, is that each vertex also had its own local information. Everybody has its own distance vector, which sort of makes this decentralized. There's not this one, sort of omniscient entity sort of sitting above the graph, looking at everything, routing which way things should go. Everybody can make its own independent decisions. Okay? So, but now the question is this algorithm fault tolerant, as we've described it? What would happen if we suddenly introduced, a change? I don't know. Let's go back up to the graph. And so suppose we no longer have a connection between X and Y. This link is broken. The Ethernet cable malfunctions, and we can no longer send messages directly from X to Y. Is our algorithm going to pick up on that? Well, maybe. If we're already at the end of round 3 and we've seen that these distance vectors had converged and we've got the shortest routes and we stopped doing these exchanges, are we ever going to incorporate that information? That somehow our graph has changed, our connectivity has changed? No, we're not. Now, what if devices X and Y had changed while we were still doing the exchanges? Let's say back up like after round 1. Would we pick up on that? Yeah, because we would have immediately known device X is going to know it's no longer connected to device Y. So would it be sending out those estimates saying, hey, I've got a cost of, or a path of cost 2 to get to Y? Would it be sending people that information? No, it wouldn't. So the idea is, if we were still exchanging our distance vectors, we would pick up on the change in that graph immediately, and eventually, it's going to take a couple rounds of exchanges, but that information is going to propagate its way throughout all the other devices. So was our algorithm fault tolerant? Not quite, but with a simple extension. Just don't stop exchanging distance vectors. Even if they've already converged, we've found those shortest paths, keep doing that periodic exchange of distance vectors because the graph might change. And the moment that graph changes, the individual devices whose connections were altered are going to detect it. They can then update their estimates accordingly. And then as these distance vectors get exchanged, that update is going to then sort of propagate throughout the entire internet. And people will eventually update their own distance vectors to say, oh, I shouldn't bank on that connection being there, and find a different path if it was included in some of the shortest routes. Okay? Does that make sense? Okay. So do we now have our decentralized and fault-tolerant algorithm? Sure. Okay. Well, that wasn't too painful. So some other generalizations that we might want to consider. In this example, we'd always looked at the exchanges were happening synchronously, that there was a total round of exchanges where X and W exchanged and X and Z exchanged. Everybody sort of did this at the same time in synchrony. That doesn't have to happen. We could have devices just at random times or just completely decoupled from each other send distance vectors. So for instance, like does the wireless router here, is that updating quite a bit in this classroom? Yeah, probably about every hour to hour and a half, because every time a class ends and you take all of your cell phones and tablets and laptops out of the room, is that changing connections? Yes. And so do we probably want the distance vector on that wireless router to update more regularly? Yeah, because there's changing connections. Deep within the infrastructure, so within the Stony Brook network, so go over like by the servers over on West Campus, where they're, or like the west side of campus where they're stored, is the connectivity there changing as frequently when you've got a whole bunch of servers that are hardwired together? No. So do those distance vectors necessarily need to update at the same frequency that the wireless router might need to? No, they probably don't, because things aren't changing that much. And so we might program that into the devices, and instead of having all of this synchronicity between all of the exchanges, we can take advantage of sort of having some idea of what's going on in the internet. Exactly. So the things that the humans are interacting with, where we know that the connectivities are changing, are going to need to update more frequently. So something like the endpoint routers, especially wireless routers and just different Wi-Fi networks, are probably going to have to update much more frequently than things that are hardwired together. Yep. But we can do that. That's not a problem. The other thing we can do, and in fact that is done in the internet, is they're actually going to coarse grain a lot of things. So in our example, we said every device had an element on the distance vector. Okay, again, how many devices are there on the internet? I have no idea what the answer to that is, but it's probably at least 9 or 10, if not more, digits long. Okay, we're definitely in the billions, if not more. Does every device on the internet need to store a distance vector that has, I don't know, 20 billion entries in it for how to route things? No. And so what we might do is we might try to coarse grain the internet. Again, thinking back to our example that we did a little while ago, if we were to send a message to Australia, do we care whether it's going to Canberra or to Sydney with regard to immediate routing? Which device do I hand it to? When we're here in New York, does it matter whether the ultimate destination is Canberra or Sydney? No. We know we need to get it up to our regional ISP, to hand it to the global ISP, to hand it to an Australian regional ISP. That person might then care, is it going to Canberra or Sydney? But until we get to that level, does it make any difference? No. And so we can coarse grain. And so maybe one of the things that we've done on our distance vector is we say, well, what are the things that are local to our network? And those might actually get individual elements in our distance vector. Things that are more regional, we say, well, we know this is going to have to go to our regional ISP. Just send it there, and there's just maybe one element on our thing for what's the way to get to the regional ISP. At which point, we just send it there, and then the regional ISP would then figure out, okay, well, do we send it over to some other network, or do we forward it up to the global ISP? But we can coarse grain the internet to try to keep the number of elements in those distance vectors fairly small, because if the destinations are really far apart, a lot of the paths for some closely related things are going to be very similar at the beginning. And so we don't need to store a whole bunch of that in that local distance vector. And so this coarse graining, anytime we make sort of one of these groups, is what will be called an autonomous system, if you go looking up how the internet works, if you were curious. But that's about it. So does anybody have any questions about route finding on the internet? Okay, so to summarize up, basically the internet, it's just this whole big network of digital devices that are interconnected and try to exchange data. Again, despite what a senator said 10 years ago, it's not a system of tubes. So the internet uses protocols to make sure that the devices are communicating in intelligible and predictable ways, so that we know if you're given a message, here's what's going to happen, here's the response. They try to deal with all sorts of different outcomes, and we saw that there were error messages built in. Something went wrong, can we redo this? Or here's what went wrong, you should know. There's error diagnostics built in. We also have layers within the internet that help translate the different things that we need to do. From saying, we clicked on some new link, we need to go get that web page, to actually parsing that and sending requests, to actually figure out, within my computer which application is talking and divide everything into packets, to sending it into the network layer, into the internet to actually get routed from device to device, where all of these layers basically sort of help us understand what the internet's doing and provide a good problem-solving strategy for sort of divide and conquer and doing triage. Who's responsible for what element of this? The network layer, when we're routing those packets through the internet, doesn't care whether it's sending website information, computer viruses, or anything else. All it knows is there's data that needs to go from here to here. Okay? It's up to the other layers, the transport layer and the application layer, to figure out what all that means and where it should go within a computer. And so then the key thing that we discussed today is, the internet is huge, and so we need these decentralized algorithms to do route finding. And so part of the decentralization, we discussed DNS servers last time. Why did we not want a centralized DNS server, besides the fact that the internet is really huge? Well, it's constantly changing, sure, but there was maybe a more philosophical reason. Who do you trust to maintain it? I trust me. I'm the only person I trust. You shouldn't trust me, and I don't trust you. Okay? Therefore, we have lots of DNS servers, and figuring competition is a great way to make sure everyone's staying honest. Okay? And we also saw that decentralization when we were doing our route finding. And so I think, quite frankly, the neatest part about all of this is at the end of the day, there was very unsophisticated math, saying, like, here, look at a potential route and look at which one has a smaller cost. That's basically all we needed to be able to do this. There was no calculus required, none of this. But yet, this simple algorithm really is how the internet works. So again, I hope I've convinced you that the internet is completely held together by bubble gum and paper clips. This is not an exaggeration of what's going on. Okay? So this basically concludes our final lecture. This sort of ends the last unit. And so just wanted to recap sort of what we've been doing all semester, what you've been doing in your term papers of looking at a technology. We can try to figure out some model and bring in some math concepts to help us understand it, and then try to bring those math concepts back in and answer some important questions about the technology. The main goal of doing all of this has really been to develop critical analysis. I recognize you're not all applied math majors. I recognize not even all of you are STEM majors, and that's fine. But the idea is you can take these problem-solving, these critical analysis skills, and apply them to whatever it is that you're going to study and whatever it is that you're going to do. And I hope this class has helped you develop those. Just as an overview for the next couple lectures, so next Wednesday on the 6th, which is the last lecture, we'll discuss the final exam, grades, and all of that. I'm not going to have much to say before then because we're probably not going to be done grading everything much before then. The next 2 classes, this Wednesday and next Monday, what we're going to do is sort of showcase what I'll call research vignettes, where I'm going to have different Stony Brook faculty come and tell us a little bit about their research to see how they can use modern technology, a little bit of applied math, and do cutting-edge research, brand new things. The goal of this is I'm trying to show you, this is at Research One University. I'm sure you probably knew that already, but what that means is there's lots of world-class research going on here. There is really cool stuff, and I want to try to convince you that you have the tools and the skills to participate in it, if you're so interested. Again, whether that's in something like science and tech and math, that's fine. If you're interested in philosophy or English or linguistics, there is phenomenal research going on in those areas too, and you absolutely have the skills to participate. And so I want to bring a few people here to show you about some of the things that they're doing, and maybe this might inspire you, and if it's something you're interested in, you can talk to them or talk to other faculty members and get involved if that's something you're interested in. Otherwise, that'll be where we draw the line. Remember, the homework is due on Wednesday. Have a wonderful afternoon, and I will see you in 46.5 hours.